Hey all, my name is Chris Saw and I work in the Theos group of Nicola Marzari in the EPFL Switzerland. And today I'd like to tell you about the work we've been doing to develop common workflows for computing materials properties using the AiiDA platform. In this talk, I'll be taking you through what the AiiDA platform is and how we use it to create workflows, how we built on this to create common interfaces for multiple simulation codes, and finally, how we made these workflows both easy to use for non-experts, but also fully configurable for advanced users. So what is the problem we are trying to address here? Well, the prediction of materials properties, in particular using density functional theory, has really grown of interest over the years. This is in part due to the rapid increase in the number and size of computations that we can now run, but also alongside this, the steady increase in the diversity and robustness of available simulation packages and theoretical methods, which has allowed scientists the possibility to really select the optimal capabilities for their research. With all this added power, we can now think to apply large-scale screening studies for the discovery of materials with optimal or novel properties. High-throughput computing, though, comes with its own set of challenges. The first one is workflow automation. We need to have the tools to be able to define and manage complex workflows. And we would also like these workflows to deal with simulation failures for known failure modes. At the same time, you don't just need the workflows, but you also need to have an engine where the workflows can run in a robust way. And when you're doing this, you need to manage all the data which is produced, not only to store it in an efficient way, but also to make it easily explorable. An important point for us also is the one of reproducibility, that you store enough information in order to be able to fully reproduce any computational workflow. And this really feeds into the fair access to data and computing. In order to address these challenges, we created the AiiDA platform. It's an open source Python package to compose and run workflows, which provides a number of features, including a scalable workflow engine, automated tracking and storage of data, built-in support for interfacing with compute resources. So it will automate submission and retrieval of simulations on any supercomputer facility. And it has a flexible plugin system for extending the core functionality of AiiDA. The core design idea of AiiDA is to represent the full history of any piece of created data, known as its provenance. Very simply, you start from the concept that any calculation connects a number of inputs to a number of outputs. And now, if you imagine that any output data can also be the input of another calculation, you end up with a directed acyclic graph that can describe multiple steps of a complex workflow. AiiDA itself is not specific to material science, but if we take the example of a material properties workflow, you could imagine taking some initial atomic structure and running it through a number of computational steps to compute a certain property. This graph shows you the basic concept, but when you look at real provenance graphs as created by AiiDA, they can look something like this. So they are very easily quite complex, not because we represent things in an overly complex way, but that's just really what we do as material scientists. When you run, say, a molecular dynamics simulation, you may have to do lots of runs, some pre-processing to prepare the structure, maybe a mix of DFT with some classical method, and so on. And so the graph, which represents the inputs and outputs of every calculation, becomes quickly very complex. At the bottom here is a graphical representation of an actual database with calculations of basic electronic properties of around 500 materials. So this is not particularly a high throughput study, yet the amount of connections you have in the database is already so large that it's essentially impossible to reconstruct later. Even the most diligent scientist will not be able to fully reproduce in detail what has been done and describe it in a paper. So you need to have a tool like AiiDA that tracks this provenance while the simulation is run and stores all the metadata for the calculations. As I mentioned, AiiDA has a pluggable framework. And by that, I mean that you can create your own Python package and use the Python entry point system to declare new components, such as data types, calculations, and workflows, which can then be loaded by AiiDA in run scripts to compose and submit computations in a very standardized and modular way. To give you an idea of what this looks like to implement, I have, for example, a Quantum Espresso code plugin to tell AiiDA how to generate the input files, how to call the code, and how to pass its output files. A structural relaxation workflow on the left, which calls the Quantum Espresso code, plus handles automatic restarts on failures like reaching the wall time. This can then be used as a component of a band structure workflow in the middle, which you can load via its entry point in the script on the right. When we run this script, it creates our provenance graph, and you get out some final result, like so. To help make these plugins discoverable, we also created the AiiDA plugin registry, where anybody who has been developing a plugin can add it for users to find. We now have a community of many plugin package developers providing different types of plugins with lots of workflows focused on computing different materials properties across the different materials simulation codes. But having a code plugin and standardized data formats is only the first step. What we really would like to achieve is to have some kind of turnkey solutions, turnkey workflows. And here I'd like to make an analogy with cars. If you have a car and you want to drive to work or drop your kids off at school, etc., you don't want to have to be the expert of an engine to know which pipes to connect to what. You just want to be able to get in, turn the key, and go. What we want then is to have something where I press a button and it runs a simulation as simply as possible. Not only runs it, but also that it's reliable and robust. We don't want our car's engine to break, and in the same way, we don't want the calculation to fail. To drive a car, you still need a driver's license. And similarly, we still expect users running simulations to have some basic knowledge of what our crystal structure is, what properties are being computed, and what are the limitations of the methods we are using. But then, like changing a car, we don't want users to have to learn how to run a simulation again when switching between simulation codes. At the end of last year then, we published the first common workflow paper, which is an initial implementation of our solution to compute materials properties using 11 different quantum engines, an effort which started with a few codes, but quickly was open to many more contributions. You see here all the simulation codes that are involved, and everything we did is fully open, both in terms of the data generated, but also the codes and workflows to create it. The key idea is that, let's say I want to compute a material property, then now it is possible to just run this command line at the top. I ask the AiiDA Common Workflow tool to launch an equation of state computation with, say, the siesta code on the aluminium crystal structure. Then we have a protocol to dictate the choice of numerical parameters, which hopefully, for precise, gives some kind of relatively high level of accuracy. An important outcome of this is now I can just change the strings for any of the other 11 codes or another crystal structure. Just press the button again, and the result that we will get will be something like on the right, where hopefully everything agrees. Note that I didn't have to tell the tool any exact parameters to use. In order to determine these parameters, as opposed to defining all possible parameters for any code, we went for a more practical approach. We simply define a set of protocol strings, fast, moderate, and precise, that every code will have to implement. It is then up to the code-specific expert to choose such parameters, with the requirement, at least for the precise protocol, that results should match within a certain level of precision. The protocol is just a human readable name, and in our supplementary information of the paper, we tried to give a concrete description to the expert of what is required. Since this is all run in AiiDA, you can then also go back and check exactly every numerical parameter for a simulation. I can tell you that at the beginning, when we started this project, many of the output plots we produced were very much not in disagreement. But by iterative discussion, together we managed to align them and essentially to find robust choices of initial parameters. This, however, is not enough. It is highly likely for almost any of the simulation codes, there will be a number of issues you might encounter. Some are relatively basic, like the wall time of your supercomputer was reached, so you have to restart. But there are a number of other things, like a self-consistent calculation is not converged, or the diagonalization method crashed, etc. For each of them, an experienced researcher for that code often knows how to fix the problem, how to change the parameter in most cases. This can be automated. And I stress that this fixing of errors is very code specific. AiiDA makes it easy to define error handlers, which we just cite error by error, how to fix it, what inputs to change, in order to try to achieve a successful result. Implementing it is then up to each of the 11 or more plugin developers. Putting together automatic parameters and robustness is a good start, but it's still not enough, because every code will have different ways to specify any inputs, different output formats, different routes through which the workflow goes. And this is not an easy thing for a person to switch. Just to give an example, here are some real graphs using Siesta and Quantum Espresso for the atomic relaxation workflows on the left, and then on the right, when these workflows are used as a component of a larger equation of state workflow. You see here graphically that even the topology of these graphs are different. And so what we did in the next step is to define a common format for the inputs and the outputs. We defined a very small set of mandatory inputs for a crystal structure relaxation, which was the first common workflow interface we defined. We just need to define the crystal structure itself, of course, a protocol string, the type of relaxation you want to do, fixing the atoms or the cell parameters, etc. And finally, define the engine. So this means which code on which computer you want to run and with which CPU resources and in what maximum wall time. We also standardize a set of optional but standard metadata inputs. So things like thresholds for forces and stresses, the electronic type, if you know it's an insulator or metal, the spin polarization, if you want to use magnetic systems, and in case you want to study an anti-ferromagnetic material, you can already specify in a common way for all these codes how to specify the initial magnetization per site. At the same time, we also standardize, of course, the output, because once you can run it, you also need to have a way to easily understand which simulations will run. So things like forces, stresses, total energy, relaxed structure at the end, and the total magnetization are all standardized. A final goal I mentioned was to make it both easy for a non-expert to run and customizable for expert users. The practical solution we came up with in the design implementation is splitting the common workflows into two. So we have common inputs at the top and common outputs at the bottom. on the outside. Then the core workflow that we also call work chains in AiiDA is going to be code specific. This could be maybe a siesta atomic relaxation. The only requirement it has is to produce the output in the common format. But the input can be anything it wants. It can be very specific and very detailed. At the same time, the second requirement we have is that any of these workflows comes together with an input generator. And this will take common inputs and will generate any output needed to be then directly passed through to the workflow. So this kind of two-level design achieves what we call optional transparency. A non-expert user would just use the two as a black box. We just set the common inputs, take whatever the input generator generates, pass it to the relaxed work chain, and then look at the common outputs. But an expert user could then go in, look at this intermediate output, and change them at will with anything they want. How does this look like in the code? So in Python, you essentially just load the specific workflow implementation, grabbing here the siesta common workflow. You import the structure in a way which is the same for all codes that can be from a file, from a database, etc. Then you just specify again in a common format which code you want to run, how many nodes, and what is the workload time. And then you can just call this input generator that I was mentioning, which takes the outputs and generates what we call a builder, which essentially has wrapped all the inputs where you pass the structure, the engines, and the protocol, and possibly other optional inputs. Now, if you're a non-expert, you can just submit it. Or if you're an expert, you can go here and add some lines to modify the inputs in the builder. So now the question you might also have is, does it work? Is it possible to really make it work for 11 different codes? And the answer I would give is yes. I want to stress, in the first paper, the goal is not about demonstrating numerical accuracy, but more to demonstrate that the concept works and is possible. As I'll mention next, we're now in the process of making a more stringent set of validations using a range of oxides. What we did here was just to pick one example per category: an insulator, a metal, a more complex crystal, and a magnetic system. These are the results you get then for all the different codes. And as you see, they're maybe not perfect, but already in very good agreement. Now we have this initial working implementation. I want to briefly mention the future plans for the second phase of this collaboration. We're trying to achieve a number of different goals. The first, we are adding a number of new codes. Next, we are extending and increasing the number of common workflow interfaces and implementing them for different codes. I'd stress that each of these common workflow interfaces requires sitting down and agreeing on what is the format of the inputs and outputs for bond structures, density of states, etc. And so, of course, it's also not only the implementation, but importantly also a design of how the input and output for each of these common workflow interfaces should look like. We are already looking at band structures, density of states, and possibly projected density of states. Then also Born effective charges and the electric constants as ingredients to the actual common workflows for phonons. The other important thing mentioned earlier is the desire to create a more stringent cross-validation of these codes. So what we will do is take a set of 6 oxides per chemical element for most of the periodic table. We'll run the equation of state for all of the codes and oxides, compare them, and try to understand if there is a margin for improvement. Many of the codes also have co-developers involved. So we're very optimistic that this collaboration will really help not only validating the accuracy of the code, but also implementing automatic recipes for anybody to run the code at that level of accuracy. The final topic I want to touch on is that of accessibility. Putting these workflows and the data they produce in the hands of users, making it as easy as possible for non-experts to analyze, reproduce, or extend our results. So the first thing we did was to release everything inside what we call the Quantum Mobile. This is a virtual machine we maintain, which among other things contains AiiDA. It contains all of the quantum codes I mentioned that have an open source license. It contains all the data plugins and workflows, including the common workflows and its command line tool. Within this, you can just run the command that I was showing earlier, running here with a Quantum Espresso silicon equation of state with the fast protocol. I submit to the AiiDA daemons, which means AiiDA will run it for me in the background, running or queuing the various jobs. And this can run on your laptop, or you can also easily interface with a supercomputer. Then at the end, you can just run a command and it will show you the results. Since it was run with AiiDA, you also automatically have all the data provenance stored for you to inspect. This is exactly what we use to run the tests and generate results for the paper. Then we could use AiiDA to generate data archives and publish these on our Materials Cloud online repository, together with all the scripts to reproduce it. So if you go to this specific URL, you can actually look at it. You can download everything in the AiiDA archive file and perhaps even import it into a Quantum Mobile instance to explore locally. Alternatively, the Materials Cloud platform also allows you to explore the data graphically right in the browser, actually using the AiiDA REST API in the background. You can, for example, go and look at all the exact inputs each of the implementers of the workflows decided to use. So here I'll just pick 3 different simulation engines. If you know one of these codes, you would hopefully recognize the inputs. All are very different, but achieve essentially the same output goal. Building on the API and command line interfaces, I note that all this has been designed with the idea that it can be used in a graphical user interface. All the inputs and which inputs are available to each code is machine inspectable. And so it's very easy to convert it to a graphical user interface. What we are looking to do in the future is to add common workflow interfaces as an app into our AiiDA Lab platform, which is a web-based interface for AiiDA built on top of Jupyter. This interface can then be deployed in a scalable way for anybody to access. With this, I'd like to conclude. I just want to thank all the people who have made this possible. First of all the AiiDA and Materials Cloud teams, all the people contributing to AiiDA and the various plugins, all the authors of the Common Workflow project, but also the new collaborators who are now working together for the next generation of common workflows. I'd like to thank also the funding which made this possible. In particular, the NCCR Marvel in Switzerland, the Max European Centre of Excellence, the Swiss Universities Fund, and a number of other European projects, including Marketplace, Dome, Intersect, BigMap, and NFFA. Finally, I want to conclude by summarizing the Common Workflow project status. We have already implemented and delivered open source, robust, turnkey workflows for materials properties, with a common interface across 11 quantum engines, and more will be coming, which are very easy to use, but at the same time, flexible for experts and designed to be interfaced to graphical user interfaces. And this will be the basis for verification and validation studies for the oxide set and the starting point for more common workflows. And with this, I thank you for attention and I look forward to conversing with you in the future.